I'm here. I feel very great to be here again. This is my second Congress, and we are talking about nanomedicine for Alzheimer disease that is compounded by traumatic brain injury. And as you can see that this is the collective work of so many people. Dr. Muratano is from Romania, Dr. Enrique is from Spain, Asia from United States, and Dr. Tian, Dr. Manjulu from Russia, Dr. Patnaik from India, Mosca from Austria, Nojali from Harvard University here, Kastilani from Bethesda, and my wife Sharma is here. So before I go there, this is one of my colleagues, Dr. Stephen Skapper. He was chief editor of CNS Neurological Drug Targets, and he passed last year, and this is the tribute to him. Whatever I'm telling to you is my personal opinion, and it has nothing to do with any organizations or government organizations we are working with that. So the military personnel are often very prone to traumatic brain injury, and traumatic brain injury is one of the leading factors in developing Alzheimer disease, and that is well known, even Parkinson disease, but this time I'm talking about Alzheimer disease. And the problem is that all kinds of neurological disease opens the barrier, and there could be accumulation of amyloid beta peptide and tau proteins. They are also accumulated in traumatic brain injury. So this is one of our recent papers published a couple of years ago, telling that Alzheimer is really a problem, and it is developing in the developing world and in almost all parts of the world. Just I'm showing here that this is one of the examples where this is normal brain, and you can see that in Alzheimer disease, how much brain tissues are lost and the tissues are gone as compared to the mild cognitive impairment. So there must be some differences between mild cognitive impairment and Alzheimer disease. This is another cartoon showing that in Alzheimer disease you have loss of temporal cells, and the ventricles are very much lost. And this is one of the reasons that our many sensory and motor functions are disturbed in Alzheimer disease. This is just an example to showing that recent paper that military risk factors for Alzheimer dementia and neurodegenerative diseases, and risk factor for traumatic brain injury and post-traumatic stress disorders. They are very much linked. And then I'm showing that you might be knowing post-traumatic stress disorder when veterans are returning after the war zone, they have severe problems, and many other kinds of problems occur. And this was the 2018 publications that even we can fingerprint in traumatic brain injury, post-traumatic stress disorder, and post-traumatic stress disorder plus traumatic brain injury are. This is an example. This is amyloid beta peptide, and this is the normal cases. This is the brain injury. You can see these are much more higher, and this is, you see, like post-traumatic brain disorder and post-traumatic brain disorder plus traumatic brain injury. So each cases are different, and amyloid beta peptide shows different level of distribution. So we can really pinpoint that whether this is post-traumatic stress disorder, whether this is traumatic brain injury alone or combination, or even Alzheimer disease. Now the question comes that whether this is healthy control and post-traumatic stress disorder, where they can be localized. And you can see that there are different reasons. Again, this is post-traumatic stress disorder, this traumatic brain injury, that has the most severe accumulation of amyloid beta peptide as compared to healthy controls. In healthy controls also we have some amyloid beta peptide, but normally they are not present in the brain. Now the question comes, where are the deposits? Whether it is in whole brain or specific areas, and this shows that this is frontal cortex, cingulate cortex, and this is parietal cortex, temporal, and occipital cortex. You can see this is normal, and post-traumatic stress disorder, traumatic brain injury, and traumatic brain injury plus post-traumatic stress disorder. You can see by yourself that there is a wide variation of deposition of amyloid beta peptide as shown in SUV, standard active values for 5 brain lobes. Now, a paper published in Proceedings of National Academy of Science in 2018, it shows that plasma factors do regulate the traumatic brain injury and even Alzheimer's disease. Why? They have demonstrated that depletion of blood plasminogen is sufficient to protect against both immune cell activation and Alzheimer's disease. When they have modified this, they can show that Alzheimer's disease is well protected. This is an experimental study in mice. Now, people are not talking about much leakage of blood-brain barrier in Alzheimer's disease, but they are telling that probably the efflux of amyloid beta peptide is reduced. But we believe since long time that blood-brain barrier could be the key, and this paper was completely ignored. Although this was published long ago in 1968, one patient, mild Alzheimer's disease, showed leakage of plasma albumin from Maastricht University. This shows, but this paper was ignored. When we did to test our hypothesis, this was probably the first experiment in which we have shown that leakage of endogenous albumin in mouse brain. And when we have used cerebrolizin, a multi-model drug that is produced in Austria, and we have clinical trials in the United States of America, that it is able to reduce it. Then we have measured the same thing, amyloid beta, and you can see that this is normal, this is modified mice, and then we have given cerebrolizin. But the most important point is that when we have used nano delivery of cerebrolizin, we have much better effect than the cerebrolizin alone. Then we also try to verify our hypothesis using phosphorated tau, and you can see that this is the highest level in APP mice, and nanovirus cerebrolizin was the best to reduce it. I will come later on about nano delivery. So the point is that do we have further exacerbation when we have traumatic brain injury, and that can also exacerbate the pathophysiology of Alzheimer's disease. Then we have used animal model of head injury. I'm showing you later. And then we have used even mesenchymal stem cells and also cerebrolizin combination. Because in lifetime, either you have two kinds of things. You combine two treatments, either it will exacerbate the beneficial effects or they will neutralize each other. But I'm talking only the synergistic better effects of these combinations. So this was our model. This amount of weight was brought over the right skull comfort representing the height. It produces 0.224 Newton impact, which is moderate by any count. And you can see here that we have severe neuronal cell damage on the right side as well as more damage on the left side. So our model represents counter-acute phenomena. Regarding head injury in military, this is quite complicated problem, and I'm showing you the data from US military organization that penetrating could be 3,877. Altogether were 244,217 from 2012 to 12 years. And you can see here also there are differences between ages, male versus female. So this is quite complicated and still not well treated situation in any kind of population, especially in military. Here the data show that if you have concussion, then your working memory and network processing capacity is decreased, even more planning as well as compared to the healthy situation. These are the techniques I will explain you later, and we are advocating use of nanotechnology in Alzheimer's disease, but we are not the first. So what we have done, we have used mesenchymal stem cells, about 1 million, and then we have used cerebrolizin with nano delivery, and these are the TiO2 nanowires on which the cerebrolizin of the mesenchymal stem cells were labeled by University of Arkansas, my colleague. They have the US patent for doing that, and this is Dr. Ryan Tian, who is doing at University of Fayetteville, Arkansas. So this is Dr. Ryan Tian, our colleague, and this is Dr. Van. They have the US patent of titanium dioxide nanowire and loading of drugs. As you can see that even stem cells can be nanowired, and this is one of the examples that the silicon nanowires can get in mouse and develop the stem cells, and they live longer and produce much better results than alone. To shorten time, I'm just showing this table, and it says that traumatic brain injury results in beta-peptide diffusion in this brain pathology, and after nano-delivery of mesenchymal stem cells and centralized. So this column is peripheral value breakdown. This is brain edema, of course, and this is neural injury, and beta-peptide deposits, and number of albumin cells in the brain. So only saline infusion and amyloid beta-peptide infusion. The values enhanced significantly. When we have added traumatic brain injury to this, the values were almost doubled in all forms. Cerebrolysin alone, the values were reduced both in ABP infusion alone and traumatic brain injury combined. Mesenchymal stem cells also, they work alone much better, but when they were combined, we have one of the best effects in both the cases, all parameters. So what are the evidences at microscope? This is neural injury in left parietal cortex. Untreated, you can see many dark neurons, many white spaces, it's called Nano mesenchymal stem cells better. Nano cerebrolysin is still better, but the combination of two shows much better picture of consistent neurons in our model. The other question is one of the enzymes is neprilysin, and it is both reduced in Alzheimer disease and also in traumatic brain injury. So maybe if we add exogenously neprilysin, we may have some beneficial effect. And as you can see that this neprilysin is pairing amyloid beta-peptide, but not with associated. So this shows the same thing, that here this is amyloid beta-peptide infusion, and you get the Crowne, cerebrolysin plus amyloid beta-peptide infusion, and then we have a third factor, neprilysin. So you can see that when we have added neprilysin, we have the most reduction in the value of the Mans blue and the iodine. Also the water content was significantly reduced, and this is number of APP deposition, albumin, and neural all were reduced if we combine with the things. What are the groups about that? And you can see here that this is traumatic brain injury plus Alzheimer disease untreated. This is further enhanced in the hippocampus because we are targeting hippocampus, many large cells. Traumatic brain injury plus Alzheimer disease, treatment with cerebrolysin. Some cells were very nice, but when we have combined all these treatments, then we have much better effect than. So we feel that combination therapy could have some future. Of course, this is animal experiments, and we need to substantiate in clinical studies. But I want to make caution here that just to use nano delivery of any drug is not helpful. You should have good drugs, then their activity can be enhanced. For example, this is the homing analysis, many drug companies do this. This is the one of the best column, this is one of the worst column, and you can see that one drug, I cannot name it, nano delivery is lying in this column, laminectomy and control also lies here. But some of the nano delivery drugs are coming here, and some of are in between. So it depends on the quality of your drug. You want to have better results, then you should use not just nano delivery can make any bad drug to good drug. The mechanisms why nano delivery can induce better effects is still not clear, but based on our observations and many other literature, we believe that these nano delivered drugs can penetrate the endothelial cell membrane with very tiny holes, not damaging them, and may enter into the intracellular or intercellular spaces, and they live longer there to have better effects. And we always just our hypothesis to National Innovation Summit every year, and we are happy to show you. We have several, but I'll just show you in 2018. Co-administration of nano cerebrolysin with antibodies to neuron antioxidant synthase and mesenchymal stem cells can reduce pathophysiology of spinal cord injury, and then jury were all these organizations from the United States. We also held last year successful advances in nanotechnology in Society for Neuroscience, And just this book is out, Nano Neuroprotection and Nano Neuropharmacology, written by my wife and me. It's progressive brain research. Its impact factor is 3.6. We also have earlier books by Springer and Elsevier. So point out that combination of different drugs using nano delivery may have better effects, and it should need to have further exploration. Nanomedicine has the need of power, but nano neurotoxicity is one of the factors that we need to investigate. There are several other organizations they are supporting, especially the Hume International Peace Hospital from CGH1 in China, the Swedish government, National Center of Toxicological Research in the United States, and many other universities. I have shown you before. These are my funding agency, my collaborators, and I am from Uppsala University. Thank you very much for your time.
All right, do we have any questions? Go ahead, sir.
Yes. So, Dr. Sharma, this is Dr. Anish Trivedi from CSR Indian Institute of Toxicology Research, Lucknow, India. Very nice presentation. So I have a couple of questions. So what was the route of administration of these nano delivery of mesenchymal stem cells? So this is the first question. And the second one, why you have chosen mesenchymal stem cells over neural stem cells? Is what was the basis for that? And third one is, what is the size of titanium oxide nanowire?
Okay. The route of administration we have tried both intraperitoneally, intravenously, even intracerebroventricularly. It depends on the number of mesenchymal stem cells. Regarding mesenchymal stem cells, I worked with my colleague who is world leader in China, in Beijing, Dr. Wang, and he is also the president of Neurosteratology and published many books edited by us on the list. So we have long collaboration with China since 1970. So we learned that mesenchymal stem cells could be better because they can change in the brain of any different kind of cells and they can help it. And also literature supports this. So at the moment we have using mesenchymal stem cells because this is very costly and they are very huge experiment. So at this time we are concentrating on mesenchymal stem cells. And third question, the size. The size we have published, I don't remember because it's all done by my colleague in University of Arkansas, Fayetteville. But we have published 2 volumes, 2 papers in methods, and this is the first author is Ashiya Oskisek. You can find it also in my name, and they are in Handbook of Neuropharmacology. And this is well standardized technique, and I think the length could be 1 micrometer or something like that, but the width I don't remember. But you should find from the literature. Thank you for your questions. Yes, sir.
Go ahead.
Very nice work. Just, the issue in Alzheimer's disease and traumatic brain injury, in terms of really coming up with what you said, a good pharmacological approach, is a big failure up to today.
Yes, that's right.
And I don't think we understand. I work in big pharma, and we chase, secretaries, cholinesterase, and amyloid beta, as a matter of fact, is it a cause or is it an effect? It could be actually some theory that amyloid beta is a protective. It just accumulates to protect the neuron from further damage. So nobody understands it. And that's a mystery to me. It's very frustrating. And we, the scientific community is in really literally big failure. And the preclinical models have nothing to do with the disease. And even, you said plasminogen. Plasminogen, it could be just secondary effect. It's not a primary effect. So we are a plus. I really appreciate your effort in moving all of these critical. But I like your caution. That even jumping into nano and putting anything into nano, if the target is mediocre target, which is on all of the targets so far is mediocre. This is very frustrating for me. Actually, in the cardiovascular, we made a huge advances. In oncology, is a miserable strategy. Alzheimer is another miserable effort being done. So, but this is any effort in those directions. But we have to be very critical.
Yes.
Very critical. Not to celebrate things based on the mice, and the stuff like that. Histopathology, all of these things are meaningless.
Yes, that's right. I should say on this or?
No, yeah.
Okay, please.
What's your question? You mentioned that the Alzheimer's disease is characterized by the breakdown of blood-brain barrier.
Yes.
So in that case, is nano is still a significant carrier.
Yes.
Perhaps the micro will work equally well.
There are certain differences between micro and nano because you know the people from chemistry knows much better if any molecule is like a smaller to the nano level. Many factors are altered. That is not found in micro level. For example, it's zeta potential and it's moving into the space. So these are very important. So that's why we stick at the moment to titanium dioxide nanowires because they are a scaffold. They can bound the drug and release just like mini osmotic pump in the brain. So that is one of the reasons we are considering at the moment, and this is very expensive. So we cannot change so many nano materials. So that's the point.
Another point is about the stem cell.
Yes.
So just like you mentioned that there's nano delivery of stem cell. I was wondering how big is a stem cell? Can it be squeezed into the nano matrix?
No, the nanowires can penetrate to the stem cells, like any endothelial cells. And if we have commercial or even produced in Beijing by my friend Dr. Wang, the mesenchymal stem cells are pure, and then they were tagged to the nano wires. So they are bound like a scaffold. And when the nanowires are going into the brain or anywhere, then the stem cells are also going with that. And there are many papers published that nano-wired stem cells live longer and have much better effect. And their harmful effects are much lesser. That's why the literature says.
Okay, final question here.
Yeah. So, what is the fate of titanium oxide nanowire? Because these are the metallic nanowires, so how they will degrade in the body?
This is true for all nanowires. They do not degrade quickly. And in University of Arkansas, they operate this knee, and for better regeneration, they put these titanium nanowires inside the knee after the operation. And 6 months to 6 years, nothing happened, and the wound is healing much better and faster. But they stay inside. They are most innocuous at the moment, to our knowledge.
All right, folks, give them a round of applause, please. Now, folks, again, if you know your times, like he finished with